everyone, welcome to part 1 of chapter 7. Chapter 7 talks about the mole, and that's not this little guy that's in glasses here, but it's a way of counting numbers of atoms. Atoms are really small, so we can't simply count them, like 1 atom, 2 atom, 3 atoms. Instead, we're going to use this term called the mole, which is going to count a very large number of atoms. So we already have some, words that means numbers. Like if you had a case of sodas, that would be 24 cans of soda. Or if you had a gross of pencils, that would be 144 pencils. Or one that you're really familiar with is a dozen. Like if you buy a dozen eggs, then you've bought 12 eggs. And every teacher is familiar with a ream, which would be 500 sheets of paper. But all of these words mean a number. Like if somebody says a dozen, you know that means 12. Well, the same can be true of the mole. The mole means a number. And the number that it means is 6.022 times 10 to the 23rd particles. So this is called Avogadro's number. And again, atoms are just really, really, really small. So we will use a lot of them in every chemical reaction. And even if we weigh out a small amount in grams, that's a huge number of atoms because they are just so small. So we'll use this term, the mole, or Avogadro's number, so that we can count these really small atoms. And again, Avogadro's number just means, right, that 6.022 times 10 to the 23rd particles, that means a mole. And it can be anything. It doesn't have to be atoms. You could have a mole of puppies, and that would be 6.022 times 10 to the 23rd puppies, right? It doesn't matter. Kind of like if you had a dozen, you could have a dozen people, or a dozen eggs, or a dozen of whatever, right? But that dozen always means 12. Same with the mole. A mole just means 6.022 times 10 to the 23rd. It doesn't matter about what you're talking. So a mole is a unit that represents the same number of particles as there are carbon atoms in 12.01 grams of carbon. Mostly in chemistry, when we're going to define something, we will base it off of carbon. And in this case, that's true as well. So what they did was they took 12.01 grams of carbon, which is the molar mass of carbon from the periodic table. And if you take 12.01 grams of carbon and carefully count one by one each one of those atoms, you will get that there are 6.022 times 10 to the 23rd atoms of carbon in 12.01 grams of carbon. And what that means is, okay, we know 12.01 grams of carbon, that's the molar mass, right? So that is equal to 1 mole. And it is also equal to 6.022 times 10 to the 23rd atoms. So as you can see, we're starting to get some conversion factors here, right? The mass of carbon will equal 1 mole. 6.022 times 10 to the 23rd atoms of carbon is equal to 1 mole. And so we're going to start using these in order to do some calculations as we move forward. But again, the whole point of using this number is so that we can count how many atoms or molecules or whatever it is that we're using. So again, it doesn't matter what we have. If we have a mole of carbon, then we have 6.022 times 10 to the 23rd carbon atoms. Or if we have a mole of gold, we have 6.022 times 10 to the 23rd gold atoms. And again, like if we had a mole of puppies, right, that would be 6.022 times 10 to the 23rd puppies. It is a way of counting something, right? And usually we use a very small amount of it, right? Something that's very, very small, like atoms. So if we have a mole of aluminum, we have 6.022 times 10 to the 23rd atoms of aluminum. A mole of iron would be 6.022 times 10 to the 23rd atoms of iron, right? And so these are both elements, right? Aluminum and iron. So that's why we're using the term atoms, because they're elements. As soon as we get into things like water or vitamin C, right, now we have more than one element bonded together, right? So we've made compounds or molecules. And so instead of using the term atoms, we'll use the term molecules. But they're going to be calculated exactly the same way. The only thing that's changing is that when we have, a compound, right, we have not just one element, then we're going to use the term molecules, like this, like vitamin C, more than one element. And if we have just one element by itself, then we'll use the word atoms. So Avogadro's number, 6.022 times 10 to the 23rd, can be written as an equality. And our equality is that 1 mole is equal to 6.022 times 10 to the 23rd particles. And again, those particles, those could be atoms, they could be molecules, they could be puppies, right? It could be whatever it is. But it's 6.022 times 10 to the 23rd. And since we can write our equality, we can use it as conversion factors. So we can put 1 mole on the top and 6.022 times 10 to the 23rd particles on the bottom. Or we can put 6.022 times 10 to the 23rd particles on the top and 1 mole on the bottom. And again, that's going to be based on what kind of calculation we're trying to do. What are we trying to cancel out? So we will use Avogadro's number to convert moles of a substance into atoms or atoms into moles, right? And so in this example, we're going to convert moles of iron into atoms of iron. And so we know, right, from before, we know that 1 mole of iron will equal 6.022 times 10 to the 23rd atoms of iron. So we can write 2 different conversion factors, right? We could write 1 mole of iron on the top and 6.022 times 10 to the 23rd atoms of iron on the bottom. Or we can write 6.022 times 10 to the 23rd atoms of iron on the top and 1 mole on the bottom. And so we'll just have to see how this converts. So we're going to start, right? We're always going to start with where the number is. So we have a number in a unit, right? So we have 4 moles of iron. So that's all going to go in the beginning of our train track. 4.00 moles of iron. And I would start getting in good habits now. Make sure you include the number, the unit, and the chemical, because this is going to be important as we move later into chapter 7, but especially into chapter 9. That's going to be really important because we're actually going to change substances halfway through our train tracks. So it matters that it's iron and not something else. So we have 4 moles of iron. We'll make our train track. So if we have moles of iron in the top left, we are going to cancel down to the right moles of iron. That means that we are going to need this one on the right because moles of iron has to cancel moles of iron. So we'll have 1 mole of iron on the bottom, and that means 6.022 times 10 to the 23rd atoms of iron will go on the top. So now we can multiply the top, divide the bottom, and we will get that this is 2.41 times 10 to the 24th atoms of iron, and that whole thing is our answer. Okay. One quick note, when you're punching this into your calculator, depending on which calculator you have, some are easier to use than others. If you bought the one that I recommended at the beginning of the semester, that TI-30X2S, it has this special double E button, and it's over the x to the -1 function. So if you go grab your calculator now, and actually if you pause here and then go grab your calculator, this will make more sense. But if you look at your calculator, over that, x to the -1, there's a double E button. And what that double E button does, it stands for exponent. And we can type this number, this Avogadro's number, right, this really long number. When we type it in, we would use 6.022, and you would type that all in just like normal. And then you would hit that second function and then the x to the -1 to access that double E button. So second function, x to the -1, and that will put this E here. And that E is telling you times 10 to the. So that E takes the place of times 10 to the. And so you can write 6.022 times 10 to the 23rd as 6.022 E, and then just type 23. That means the same thing in your calculator as 6.022 times 10 to the 23rd. And the reason that this is really useful is because this function starts to mess up your calculator. And you start needing to have a bunch of parentheses, and if you're not really careful about your parentheses, you're going to get some weird answers. So it's important to make good habits now and start getting into the practice of using this double E button. And you can do it anytime you have an exponent. Anytime there's something that's times 10 to the, you can write that E button, or click that E button instead. So if we were to punch this in our calculator, we would write 4.00 times 6.022 E 23, and that would give you this answer. And so not only is it faster, but it's also going to give you a more accurate answer, and you don't need to use any parentheses. If you have a Casio, the Casio's on the bottom, one of the simpler Casios, has this button that looks like times 10 to the x. It looks like that. And you can actually use that button in place of the double E. So that will work pretty much just the same as this double E button here. So you would write 6.022, and then you'd hit that times 10 to the x, right? This is a button. And then you would put 23. Okay, and that again will give you this number. And that most of the time works. Every once in a while, it'll do something a little bit weird, which is why I like the TI-30X2S a little bit better. But the Casio, or the simple Casio that has that times 10 to the X button, that works pretty well too. If you have a calculator other than those two, then you can absolutely message me and I will tell you how to type this in on your specific calculator. Maybe just send me a picture of your calculator on Remind and show me what it looks like, and I will tell you exactly how to punch it in the easiest way in your calculator. But again, I've found that these are the two most common calculators that people have, are the TI-30X2S and that Casio. So get some practice on these. It will make your life a lot easier if you're not continually needing to use parentheses every time you type in Avogadro's number. All right, let's go ahead and try another problem. This one I'd like you to do on your own. So I'd like you to pause here, try this problem, and then once you're done, unpause, and I will show you how to get the answer. Okay. So we are trying to go, we are looking for, moles of sulfur, and we are starting with atoms of sulfur. Anytime we're trying to go from atoms to moles, that's always going to be Avogadro's number. So again, we know that 1 mole of sulfur is equal to 6.022 times 10 to the 23rd atoms of sulfur. So we can, out of this equality, we can make two different conversion factors. We have 1 mole of sulfur over 6.022 times 10 to the 23rd atoms of sulfur, or we can say 6.022 times 10 to the 23rd atoms of sulfur over 1 mole of sulfur. So we'll see which one we need to use. So we're going to start with, our number here. That's going to go in the beginning of our train track. So we have 1.8 times 10 to the 24th atoms of sulfur. So we'll make our train track. And so we know atoms of sulfur has to cancel down and to the right. So if we have atoms of sulfur in the top left, we need to have it in the bottom right. That means we're going to use this first one so that our atoms of sulfur cancel out. So we have 6.022 times 10 to the 23rd atoms of sulfur. And on the top, we will have 1 mole of sulfur. So atoms of sulfur cancels atoms of sulfur. We're left with moles of sulfur, which is what we were trying to find. And if we multiply all of that out and divide it up, we will get, 2.99 moles of sulfur. So again, make sure your answer always has your number, your unit, and your chemical. Okay. Now, hopefully you got some practice and you tried using that double E button or that times 10 to the X button, and you got 2.99 moles of sulfur. But I want you to look down at your calculator right now and make sure you did not get this, 2.99 times 10 to the 46th. Anytime you get an answer that has like something to the 46th or the 45th or something like that, that means you've done it wrong. And I know exactly how you've done it wrong is that your times 10 to the 24th actually got multiplied by that times 10 to the 23rd. And this may have come out as, 47 or whatever the case may be if it's 40 something. But it's an easy fix. All that means is that you weren't using that double E button or you weren't using that times 10 to the X button. You have two options. Go back, use the double E button or the times 10 to the X button, or make sure that there are parentheses around this whole number when you type it in. Okay, that's all that means is that you forgot parentheses and it thinks this times 10 to the 23 is actually on top instead of being on the bottom where it should be. So that's one of the most common mistakes that I see in this particular chapter is that people, are not using the double E or are not using that times 10 to the X button or not using parentheses, and they're getting this weird kind of answer. So check that, make sure you're doing it correctly. Okay, so Avogadro's number can also be used to convert molecules to moles of a molecule. Okay, and so I talked about it a little bit earlier. This word molecules is going to be used just the same way as we use the word atoms. It's just we'll use the word molecules when we're talking about more than one atom bonded together. For example, here in carbon dioxide, we have, carbon bonded to 2 oxygens. So we'll use the word molecules instead of atoms because atoms are used to refer to individual elements like aluminum or carbon or oxygen or things like that. So we have the same equality as before. We'll have 1 mole, and in this example, it will be 1 mole of carbon dioxide is equal to 6.022 times 10 to the 23rd molecules of carbon dioxide. Okay, and so people will be tempted to abbreviate this word molecules because it gets, kind of cumbersome writing it over and over again. Don't write it as M, that means mass, or MOL, that means mole. MOLE also means mole. You can do MOLEC if you like, because that's specific at least to molecules, but I'll typically write out the whole thing. So from this, we can actually write two different conversion factors, right? One of them will be 1 mole of carbon dioxide over 6.022 times 10 to the 23rd molecules of carbon dioxide. Or we can write, 6.022 times 10 to the 23rd molecules of carbon dioxide over 1 mole of carbon dioxide. So it'll be, dependent on which one we need to use and how we need to cancel our units. So we will have 3.01 times 10 to the 24th molecules of carbon dioxide. And since our units have to cancel down and to the right, if we're starting with molecules of carbon dioxide, that means we're going to need molecules of carbon dioxide down on the bottom. So we'll use this conversion factor here on the left. So we have 6.022 times 10 to the 23rd molecules of carbon dioxide. And on the top, we will have 1 mole of carbon dioxide. And when we, double check, our molecules of carbon dioxide cancels molecules of carbon dioxide, and we're left with moles of carbon dioxide on the top, which is what we were looking for. So when we go ahead and we divide all of this up, we will get that we have 4.998, or simply 5 moles of carbon dioxide. Again, double check and make sure that you're not getting, times 10 to the 40 anything, 46, 47, anything like that. As soon as you see like a times 10 to the 47th or times 10 to the 46th in your answer, you know that you've done something wrong. And the thing that you've probably done wrong is you didn't use that double E button. You didn't use that times 10 to the X button. And it's thinking that this times 10 to the 23rd is actually up here. So you would get 4.998, just at the end it would say like times 10 to the something. So double check, make sure that that is not happening to you. Okay, so here's a practice problem using moles and molecules again, but slightly different than the problem we just did. Go ahead and pause here, work out the problem, and once you're done, come back and see the answer. Okay, let's go over this. So we're starting with 1.75 moles of carbon dioxide. So that will go in the beginning of our train track. And so again, just like the last problem, we're using moles and molecules of carbon dioxide. So I'm not actually going to write it out again. We're just going to look at the previous slide. So our equality that we're using is 1 mole of carbon dioxide is equal to 6.022 times 10 to the 23rd molecules of carbon dioxide. And so we can write our two conversion factors, one with moles on the top and molecules on the bottom, the other with molecules on the top and moles on the bottom. So since we're starting with moles in this top left, we need to cancel down and to the right. We're going to need to have moles of carbon dioxide down on the bottom. So the one that has moles of carbon dioxide down on the bottom is this one on the right here. So 1 mole of carbon dioxide on the bottom and our molecules on the top. So we will have 1 mole of carbon dioxide on the bottom and 6.022 times 10 to the 23rd molecules of carbon dioxide on the top. We double check, moles of carbon dioxide cancels moles of carbon dioxide. We're left with molecules of carbon dioxide, which is what we're trying to find. So we can go ahead and multiply all this out. We'll get 1.05 times 10 to the 24th molecules of carbon dioxide. And make sure that your answer always has the number, the unit, and the chemical, so that we're being very specific. So our number, our unit, our chemical. Okay, so now we've learned how to convert from atoms to moles and moles to atoms and molecules to moles and moles to molecules. So go ahead and pause here and complete lecture worksheet problems number 1 through 5. Once you're done, come back and we will continue on. Okay, so another way that we can do conversions is we can use the subscripts in a formula to convert between moles of a molecule and moles of an atom in that molecule. Okay, so in this, NH3, this nitrogen trihydride, also known as ammonia, we have 1 nitrogen, right, because there's an imaginary 1 here, and we have 3 hydrogens. And so what that means is if we have one molecule of NH3, we just have one, like literally we could just hold one molecule of NH3. That means if I broke it all apart, I would get one atom of nitrogen and 3 atoms of hydrogen, right? If I just broke it all apart, 1 nitrogen and 3 hydrogens. So that would be if I had one molecule, it would break into 1 atom of nitrogen and 3 atoms of hydrogen. If I had instead 1 mole of nitrogen trihydride, right, 1 mole of ammonia, that means I have 6.022 times 10 to the 23rd ammonia molecules floating around. But if I broke that all apart, I would end up with 1 mole of nitrogen atoms and 3 moles of hydrogen atoms from that 1 mole of ammonia. So the subscripts are telling us a relationship between, molecules and atoms, or moles of our compound and moles of our elements. So we can use these again as conversion factors to do some fun math. First, before we get into that, go ahead and complete problem number 6. Once you're done, come back and we will keep going. Okay, so we're going to take a look at aspirin. Aspirin is C9H8O4. And so if we just had 1 aspirin molecule, then we would have 9 carbon atoms. If we broke it all apart, we would have 8 hydrogen atoms and 4 oxygen atoms. And that's shown up here. Like you can actually go and calculate it. Here's 1 aspirin molecule. And if I broke it all apart, I would get 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. And you can go through and actually, count them all. So that would be if I just had 1 molecule and I broke all the bonds and I separated them out, and then I would get 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. But if I had 1 mole of aspirin, so I had 1 mole of these aspirin molecules, right? And I broke all of those apart, which would take a really long time. Then I would have 9 moles of carbon atoms, 8 moles of hydrogen atoms, and 4 moles of oxygen atoms. So if we're starting with 1 molecule, then I'm breaking it into atoms. If I'm starting with 1 mole of it, then I'm breaking it into moles. Okay, so we can use these again as conversion factors. So here it is, just written out a little bit differently. 1 molecule breaks into 9 carbon atoms, 8 hydrogen atoms, 4 oxygen atoms. 1 mole of aspirin will break into 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So let's go ahead and see how we might use this. So this says how many moles of carbon are present in 1.50 moles of aspirin. So we're starting with moles, so we can go from moles of our molecule into moles of our elements. And the way that we're going to do that is we are going to use the subscripts here. Since I'm asking about carbon specifically, I look at my molecule and I said, okay, for every 1 mole of aspirin, right, for every 1 mole of that, if I broke them all apart, I would get 9 moles of carbon because this is C9. Okay, so that 9 ends up being here. So that's our equality. So I can write 2 different conversion factors. One of them will have that 9 moles of carbon on the top and 1 mole of aspirin on the bottom. And the other one will have 1 mole of aspirin on the top and 9 moles of carbon on the bottom. So we're starting with 1.50 moles of aspirin. So we have 1.50 moles of C9H8O4. And so we know moles of aspirin has to cancel down and to the right. So that means we will need moles of aspirin on the bottom, which will mean that we use this conversion factor here on the left. So our 1 mole of aspirin will go on the bottom, and 9 moles of carbon will go on the top. So moles of aspirin cancels moles of aspirin, and moles of carbon stays there, which is what we are trying to find. So we'll go ahead and multiply all of this out, and we will get 13.5 moles of carbon. So again, this is why it's important to include this unit, like the aspirin, right, versus carbon, because we're going to change partway through. So it's important that you're not just writing moles, or even worse, just writing numbers, because you won't know if your units are canceling correctly. So it's always important to write the number, the unit, and the chemical every single time, so that you see that moles of aspirin cancels moles of aspirin, and we're left with moles of carbon, which is what we were trying to find up here. Okay? So let's try another one. This says how many moles of hydrogen are present in 3.50 moles of nitrogen trihydride. So as you can see in this particular example, I didn't give you the chemical formula, but you will be able to write them because we just finished a chapter on that. So this says nitrogen trihydride. So the fact that there's a prefix here, that's telling us that this is covalent bonding. And we're not going to need to circle and switch. We can just use our prefixes to tell us how many atoms of each one are in our molecule. So there's no prefix on nitrogen, which means there's just one. And then trihydride tells us there are 3 hydrogens. So this is NH3. And it's asking for moles of hydrogen from nitrogen trihydride. Okay, well, for every 1 mole of nitrogen trihydride, right, we see there's a 3 here. So that's telling us that there are 3 moles of hydrogen in every 1 mole of nitrogen trihydride. So we can go ahead and we can start our train track with 3.50 moles of nitrogen trihydride. And we know that we're going to have to cancel down and to the right. And so we can look at our 2 different conversion factors and figure out which one we need to use. So one of them will have 1 mole of nitrogen trihydride on the top and 3 moles of hydrogen on the bottom. Or we would have 3 moles of hydrogen on the top and 1 mole of nitrogen trihydride on the bottom. So again, we have to cancel down and to the right. So if we have moles of nitrogen trihydride here, we need to have it down here as well. That means we're going to use this one on the right. So 1 mole of nitrogen trihydride and 3 moles of hydrogen will go on the top. Moles of nitrogen trihydride cancels out, and we're left with moles of hydrogen, which is what we were trying to find. So then we can go ahead and multiply these out, and we will get 10.5 moles of hydrogen as our answer. All right, let's go on. Before we go on, go ahead and complete lecture worksheet problem number 7. And once you're done with that problem, go ahead and come back and I'll show you how to do this with an ionic compound. Okay, here's a little bit trickier of a problem. So that was the last one was when we were asking for the number of atoms or from a molecule, or the number of moles of an atom from moles of a compound. This one, we are talking about ions, which are charged species. And the fact that it's charged usually throws people off. And I don't want you to be thrown off by it, because like here, this says how many moles of Al3+. And the fact that it says Al3+ always throws people for a loop, but don't worry about it too much. Essentially, we're looking for moles of aluminum. And it's just saying Al3+ because it's coming from aluminum carbonate, which is an ionic compound. And as you remember, anytime we have an ionic compound, that means we need to write out the ions and then circle and switch. So aluminum is Al3+, right? Aluminum has 3 valence electrons. So when it loses those 3 valence electrons, right, it loses 3 negative electrons, it's going to become a 3 positive. And carbonate is one of our polyatomics that we needed to have memorized. That's CO3 2-. And so to make this compound, right, we circle and switch. The 2 is going to go to the aluminum, so that's going to be Al2, and that 3 is going to go to carbonate. And since it needs to go to all of carbonate, we're going to put carbonate in parentheses, and that 3 is going to go on the outside. Okay, so that's aluminum carbonate. So it asks for how many moles of aluminum are in 3.2 moles of aluminum carbonate. So again, it's saying Al3+, but it's because it started off as Al3+. And actually, if you put this into water, this ionic compound would break into Al3+ and CO3 2-. But we're going to treat it just the same way as we were doing the last problem. So essentially, it's just asking for how many moles of aluminum, right? And so if we look at this, right, there are 2 moles of aluminum in every 1 mole of aluminum carbonate. So we know for every 1 mole of aluminum carbonate, we have 2 moles of Al3+, okay? Or you can think of it just as aluminum. So when we're starting off our train track, we have 3.2 moles of aluminum carbonate. And so that means our moles of aluminum carbonate are going to need to go on the bottom, right? Because we're canceling down and to the right. So that 1 mole of aluminum carbonate, 1 mole of aluminum carbonate, there we go, will go on the bottom, and that 2 moles of aluminum will go on the top. So we can go ahead and multiply all of this out, and we will get 6.4 moles of Al3+. So as you can see, we're doing this the exact same way. The only thing with the ions is that it came from an ionic compound, so don't want you to get tripped up by that. Let's try another one. This asks how many moles of carbonate are in 5.7 moles of aluminum carbonate. So same molecule here, but now when we're looking at it, we know that 1 mole of aluminum carbonate, right, see that 3 on the outside right here? That's telling you have 3 carbonates, right? We have 3 of this, 3 carbonates. So we have 3 moles of carbonate. So we can go ahead and use that in our conversion factor. We're starting off with 5.7 moles of aluminum carbonate. And we're going to cancel down and to the right, right? Moles of aluminum carbonate has to cancel down and to the right. So that means that this side will go on the bottom, 1 mole of aluminum carbonate. And that 3 moles of carbonate will go on the top. Okay, so if we go ahead and multiply this out, we will get that there are 17.1 moles of carbonate. So we can use this for, ions that are individual ions, right, like aluminum, or we can use it for polyatomic ions. But we're going to treat it exactly the same way as we were doing when it was a neutral atom as well. Go ahead and complete lecture worksheet problems number 8 and 9 to get some practice on doing these types of problems. Once you're done, come back. We just have a little bit more to go over today. Okay. Here's the trickiest one. This says how many atoms of carbon are present in 1.50 moles of aspirin. Okay, and so we haven't learned how to do this yet. You might think, well, it seems really similar to the one we did before, but we learned how to go from moles of aspirin to moles of carbon. And before we learned, using Avogadro's number, how to go from moles of carbon to atoms of carbon, but we haven't talked about how to go from atoms of carbon, or from moles of aspirin, moles of a compound, to atoms of that compound. And what we're going to have to do is we're going to need to convert our moles of aspirin to moles of carbon first, and then we can use our moles of carbon to convert to atoms of carbon. Okay, so we have 2 different conversion factors here that we need to work on. So one of them, when we go from moles of aspirin to moles of carbon, we know that we can use these subscripts to tell us how many there are. And for every 1 mole of aspirin, we know that there is 1 mole of 9 moles of carbon because of this subscript here. So for every 1 mole of aspirin, we have 9 moles of carbon. And we learned before, right, whenever we need to go from moles to atoms, that's going to be Avogadro's number. We know that for every 1 mole of carbon, there are 6.022 times 10 to the 23rd atoms of carbon. So we can do 2 separate train tracks here so that we can convert from moles of aspirin to moles of carbon, and then from moles of carbon to atoms of carbon. Okay, so let's go ahead and try this out. So we're going to start with 1.50 moles of aspirin. That will go at the beginning. And remember, we're going to try to end up with atoms of carbon at the end. So if we have moles of aspirin that we're starting with, we need to cancel moles of aspirin down and to the right. That means this 1 mole of aspirin has to go on the bottom. That's the only place in any of our conversion factors that shows up. So we have 1 mole of aspirin down here, and 9 moles of carbon will go on the top because that's what it's equal to. Okay, so we used this first conversion factor, the 1 mole of aspirin equals 9 moles of carbon. We put 1 moles of aspirin on the bottom because it needed to cancel, and that 9 moles of carbon on the top because that's what it's equal to. But now, right, we need to keep going because we're looking for atoms of carbon, and so far we've only found moles of carbon. So we will continue our train track, and we'll use Avogadro's number. Moles of carbon has to cancel moles of carbon down and to the right. So that means that this 1 mole of carbon will go on the bottom, and that Avogadro's number, right, 6.022 times 10 to the 23rd atoms of carbon, that will go on the top. Then we can double check, and we'll see moles of carbon cancels moles of carbon. We're left with atoms of carbon on the top, which is what we were trying to find. That tells us that we're done. So we can go ahead and multiply all of this out, and we will get 8.13 times 10 to the 24th atoms of carbon. Okay, but as you can see in this example, it's really important to make sure that you're writing the units and you're writing the chemicals every single time so you can make sure that they cancel out, right? Moles of carbon has to cancel, moles of aspirin has to cancel moles of aspirin. Moles of carbon has to cancel moles of carbon. And we want to be left with atoms of carbon because that's what we're trying to find. This is your way to double check to make sure that you're doing these problems correctly. If you don't have all of these units every time, then you're not going to know. And, especially if you only put numbers, you'll never know if you're doing it correctly.